Okay, thank you. So let me first start by thanking the organizers, of course, for inviting me and more importantly for organizing this conference. So indeed I'm going to speak about constructive aspect of random tensors, and the new part in my talk is a joint work with Vincent Rivasseau. So because the subject is still quite exotic among both physicists and mathematicians, so I felt the need to motivate it a bit and introduce you to the basics. So that will be my first part. In the second one, I'd like to show you the main constructive tool which has been designed 10 years ago for random matrices and more generally for random tensors. And in the last part, I will pick a special tensor field theory and try to sketch for you the proof of a very typical analyticity result. All right. So, in this first part, I'd like to answer two questions. So, why studying random tensors and how we do it. So, I go a bit fast on motivations because we had yesterday the talk of Bertrand Duplantier, who introduced the situation in 2D. Okay, so to say it in one word, the long-term goal is to have some intuition control on what could be quantum gravity in dimensions higher than 2. Okay, so let's see what happens in dimension 2. So there is a long history of interplay between 2D quantum gravity and random matrices. More than 30 years ago, it was proposed by physicists that random matrices provide a good discretization of 2D gravity, 2D quantum gravity, and they have accumulated evidence for this by computing things both in the discrete and in the continuum and checking that they match. So we've seen still another example yesterday. But there has been a lot of progress in the last 10 years, mainly, I should say, from the probabilistic side, of course with interaction with the physicists and combinatorists, etc. So there has been construction of many different random metric surfaces. The most prominent example is the Brownian map or Brownian sphere. So we saw a picture yesterday. Remember this kind of sphere with sparks everywhere. Okay, and it turns out that this random sphere is the universal limit of large planar maps. So you take, for example, the set of quadrangulation, planar quadrangulation with n faces, and you equip this with a uniform measure, and you see this as a metric space, so you keep vertices and equipped with the graph distance, and you let n go to infinity, and you control convergence in a proper topology, and it converges to this continuous Brownian sphere, which is indeed a sphere almost surely. Okay, and even more recently, it seems that there is a proof by Miller and Sheffield that the Duville quantum gravity sphere has indeed the same law as the Brownian map. So the aim is to do to try to see what we can do in higher dimensions. So I would say more generally the main motivation for random tensors is that they generalize random matrices in two ways, say. So first with respect to symmetry properties, so I will come back to this in the next slide, and also because as matrices they provide a theory of random spaces. So for matrices it's random surfaces, and here will be random D spaces. So I'll also come back to this in a minute. But to see random tensors as generalization of random matrices is not the, let's say, historical road to random tensors. So I should say at this point that very soon after people have seen that random matrices may provide the right discretization of two-dimensional quantum gravity, people have proposed very soon that random tensor could be the equivalent in higher dimensions, but not so much progress have been done until very recently, because there was kind of poor analytical control on all this, and the real breakthrough has been achieved 8 years ago by Razvan Gouraud, who modified a little bit the models and really had in this way a very good analytical control on them. And the new field is not just random tensor, but I should call them colored random tensors, and everything I will say is about this restricted field. Okay, and the historical road, I should say historical, okay, it comes from LQG, which is not Liouville quantum gravity, but loop quantum gravity. So it all came from models of loop quantum gravity. GFT is the second quantized version of loop quantum gravity. It's the group field theory. So there are field theories which are defined on copies of compact Lie groups. And in fact, tensor field theory, you can see them as both generalization or simplification of GFTs. Okay. Okay, so now let's see a bit more precisely what I'm talking about. So we'll be considering complex tensors, so namely a complex function defined on ZD, and my tensors will have no symmetry whatsoever. Okay, that's important. Nowadays we know how to deal with symmetric and antisymmetric tensors, but this is the simplest solution. Okay. So now when we look at matrix models, they are invariant under action of UN, capital N being the size of the matrix. If you want to deal with rectangular matrices, you can even have action of different unitary groups, 2. And we will require that our tensor models will be invariant under D copies of UN. It could be actually different N's. But I will keep the same for simplicity. So this is what is written here. Okay, and so I want my action to be invariant under this transformation. Okay, so how do we build invariance? So polynomial invariance in T and T bars. So what you need to do is to identify an index of a T at position I with an index of a T bar at position I. Okay, so in degree 2 you don't have much choice. There is only this invariant that I call it's written T dot T bar. Okay, and let me picture it like this. So you see there are gray dots, one gray dot which is for T, one black dot for T bar. At around each vertex there will be D half edges, so here are 4 for the example, and they represent the D indices of the tensor, and they are colored by a number, and this number represents the place where the index is. Okay, and one edge represents identification of indices. Okay, so this graph is has a lot of property. So in fact it's bipartite because I have 2 pair T and T bars with T bars. They are D-regular and they are properly edge colored, meaning that edges bear colors, numbers, and around each vertex you see one and only one color. Okay, so now in in higher degree there is more structure, much more structure than for matrices, because for matrices the only invariant you can build in degree P is trace of M to the P, let's say, So there is only one connected invariant for each degree, but here the structure is richer. So for example, in degree 4, you could have this one. So let me explain a bit. So I will start here in the upper right corner and turn counterclockwise. So we have here you see this red part, this T and this T bar, they share index number 1, 3 and 4. Okay. Now if I go on, you see that this T bar and this T, they share index number 2. Okay. We are here, etc. So I think you get the idea. So to each such decolored graph, I can associate an invariant. Okay. So as I said, there is more structure, so there are more invariants, even in degree 4. So here, for example, I could have chosen this one, and in a higher rank, you have even more possibilities. Okay, so now how can I, what look like a typical action of a tensor model? So you will have a quadratic part, which is this degree 2 invariant I showed you, and then a bunch of interaction vertices which are in bijection with these decolored graphs of order bigger than 4. So and this trace sub B is simply the notation for the corresponding analytical expression. So now we have action. Let's have a look at the Feynman graphs, which are generated by the perturbation of this action. So imagine that in your model you've allowed interaction of these two types, and we are at order 2 of perturbation, so you could have one interaction vertex of each type. And remember that vertices here, they represent T and T bars, so we are waiting now for Wick contractions. So one of these Wick contractions could be this one. So now this is a typical Feynman graph. There are two different kinds of lines. The thin gray one, they represent identification of indices, and the thick black ones, they represent Wick contraction. Okay. So now I can represent this difference between lines by simply adding a fictitious color 0 to the black ones, and keeping in mind that 0 is special. Okay. So now a Feynman graph, you can convince yourself it's a D+1 colored graph. So we had D colored graphs, they represent interaction, and D+1 colored graph, they are our Feynman graphs. Okay? All right.
I want to make sure I understand the action you have.
Yeah.
You have a quadratic one, and then I'm not quite understanding what you have
here.
Yeah, the second piece.
The second piece is so you choose for.
Is it quadratic? It looks quadratic, right?
No, it's not. It's not at all. It could be, for example, this one or this one. You choose.
Okay.
So you choose a decolored graph, write the corresponding expression, and this is your interaction.
Okay.
No, okay. So all right. Okay, so as I said,
how is it the black lines come just from the quadratic piece? Propagators that are determined by the quadratic piece in the aperture.
Yes.
Okay.
Yes. So here I say the tensor model. So usually when I say model, it means trivial propagator. Okay, but I will say theory when I add the propagator, and we'll see propagators in the third part. Okay. And it turns out that as for matrices, these Feynman graphs are in bijection with discretized spaces. Okay, triangulated spaces to be precise. So these triangulated spaces, if you have tensors of rank D, they will be of dimension D. They will represent cell complexes whose cells are simplices. They are not simplicial usually, these complexes, but anyway, so they are gluing of simplices. And here is how it works. So to each vertex of the Feynman graph, you associate a D-simplex. So here the picture is in dimension 3, okay? A D-simplex, and now to each half edge incident to this vertex, I will associate one of its D-1 faces, okay, like this. And you see this half edge bears a color. So once you fix a D-1 face, there is only one vertex which does not belong to this face, and I attribute to it the color of the half edge. And I do this, of course, for all the half edges. And in fact, what I get is that I have a correspondence between a vertex and the colored or numbered D-simplex. Okay? And now I have
just one question. The vertices, they imply the colored links and the black links, or they're only black here, black here?
no, well, you can forget. Yeah, you get
All of them there. Right?
yes, all of them. You can forget about the difference between gray and black.
But since you used black before,
Yeah.
black.
Yeah.
So, yes, I'm also confused. So, I mean, before I thought that the color 0 was for the contractions between the vertices.
No question.
Yeah. So they,
That's your question.
so they have a right. Color 0 is special in the sense that it will play a special role, of course, because they will bear propagators. So once you want to write the amplitude associated to such a graph, color 0 is special. Okay. But anyway, you can forget about the fact it's special and see that there is a bijection between these simplices and vertices.
Just repeat that these are also colored in this case. This is why you use black. So
Right. No.
you said black.
Yeah. Okay. These lines 1, 2, and 3 before they were pictured gray. Okay. But now I forget about this. The important color is the number.
I see. So I should no longer think of 0 as being the contractions in the original.
Yeah. In this correspondence, you should not. Sorry. And now you want to. Okay. So given a Feynman graph, you have a certain number of D simplices, and you want to glue them along D-1 faces, following actually the contraction pattern here. So here I have two vertices which are linked by an edge number 2. So I will glue them along the D-1 faces, which does not contain color number 2. Okay, so it should be pictured here.
Yeah, sorry, I'm still a little confused. I mean, in the simplicial picture, you should be numbering the faces then, or
Yes.
Well, it's equivalent.
well,
But because if I put color 0 to a D-1 face, there is only one point which is opposite to this face. So I decide to put the color here. Actually, it's faster for the explanation. But
What is actually the role of the colors? I mean, to any simplicial complex, I can associate a dual graph. The problem is there are too many graphs. I guess some of them are not.
no, here, yeah, right. The point is, if I forget about the colors, so you see, coming from quantum field theory, I want my Feynman graph to be in bijection with these discretized spaces. Okay, so I want to have a well-defined rule of gluing my simplices, and this is where the colors play a role, because if you want to glue two triangles together, then you have freedom. But if I want to respect colors, then it's canonical.
But it doesn't guarantee that I will get the triangulation of something that looks like a manifold, I guess.
What's the beginning of your sentence? I missed.
The meaning is that you claim that your diagrams will be dual to something like, random spaces, but these might be very weird random spaces.
Okay.
Not all looking like piecewise linear manifolds, I suppose.
So there are not manifolds in general, but they are not as wild as the thing you see in loop quantum gravity. So there are indeed singularities, So they are they are normal pseudo manifolds, and so you can have singularities. So for example, well, it's difficult to picture, but the neighborhood of a point has not a boundary which is spherical. It could be tori, for example. Okay, but okay, so no, that's right. This is not a manifold in general, but I should say, well, okay, I will come back to this later. Okay, so this colors give me a canonical way of gluing simplices. Right. Okay, so yeah.
Is there maybe in relation to your expression, is there a way at the level of the colored graph to tell if you have a manifold versus pseudo manifold?
No. It's very hard, you see, because to recognize a manifold, you need to recognize spheres, and in dimension higher than 3, it's very difficult. So if I could say by a combinatorial argument that a discretization is a sphere, well, I think I would be famous, but this is okay. Okay, so let's forget about tensors now for a moment, and we'll see this loop vertex expansion. Okay, I will try to motivate why it's so important for matrices and tensor, and then we'll see how it works on an example. So as I said, it's currently the main constructive tool for matrices and tensors, and it was originally designed for matrices by Rivasseau 10 years ago, who had in mind the construction of a very special 5 to the 4th model in 4 dimensions, but on a non-commutative space. And turns out that this model can be seen as a random matrix model, okay, with non-trivial propagator. But then very soon after this paper, which was called Constructive Matrix Theory, he realized that loop vertex expansion could also simplify bosonic constructive theory. So he wrote a second paper which was called Constructive 5-4 Theory without tears. So you tell me if you cry. Okay, so let's see why it's necessary for matrices to have new constructive tools. So there are different arguments, but they say more or less they all bow down to the following simple things. So when you have a vector model, so for example Gros-Neveu, you know that quantities of interest, so I don't know, partition function, correlation function, they are analytic in domain which are independent of this number of colors. And turns out that this is true also for matrices, but it's very hard to prove with usual constructive techniques. Why? Because one of the messages of constructive field theory is that you should not develop full perturbation theory, but only stop at trees and let the remaining contraction unexpanded. Okay, so you are allowed only to see trees, and it's difficult to recover the right power counting, the right scaling in capital N only with a tree. So let me try to explain. So in dimension 2, so for matrices you have ribbon graphs or maps. You can see them as punctured surfaces, and to each boundary component of this surface there is one free index, okay, running, and this sum over this free index gives you a factor of capital N. Okay, so if you look at Euler formula, you see that you have at most n plus 2 faces, n plus 2 boundary components at order small n. Okay, so let's say more or less one factor of capital N per vertex. Now, when you start expanding, at the beginning you have only vertices. Okay, so here I took a quartic model, so you have four free indices per vertex, so 4 n indices. Okay, and I want to go to 4n to n plus 2. The problem is that I can see only a tree, and each time I add a tree line, I will identify two pairs of indices. Okay, the pairs which are at the opposite ends of the line. Okay, so I have at the end 2n+2 indices, and I'm stuck because now the scaling in capital N is capital N to the 2 small n, and I have a shrinking domain of analyticity if I want to send capital N to infinity. Okay, so that's one point. So the loop vertex expansion should allow me to recover the right scaling in capital N even only with a tree. So that's point one. Now let's have a look at this at simplifying bosonic constructive theory, what Vincent calls sometimes his constructive dream. So let's see. Fermionic theory is easier in this respect because perturbative series are convergent. So suppose we have you look at a quantity S that you have expanded in perturbation, so you have a 1 over n factorial coming from the exponential and the sum over graphs which have n vertices. And now you want to resum this to index your series by trees. So one way to do this is to introduce 1 here in the form of barycentric weights, namely real positive numbers indexed by graph and trees, and they should add up to 1 when you sum over all the spanning trees inside G. Okay, so you have a graph G and you assign a weight to each of its spanning tree, and it should sum to 1. Okay, and now you interchange these two finite sum on G and T, and what you get is a perturbative series which is whose terms are indexed by T. Okay, and this AT, well, this is this. Now, if you are in fermionic theories, it turns out that you can prove that this AT is bounded by a constant to the n, when n is the order of perturbation. So why is it so? It's because inside a given order n, all graph amplitudes, graph amplitudes have different signs, and there are compensation at work, and you can bound this. Okay. In bosonic theory, it's not the case. Everybody's positive, okay, or well, everybody's positive, and I mean, if you repackage the things like this, then you're stuck. I mean, you make smaller packets, but they hold positive. So now the second goal of this loop vertex expansion is that it should allow a simple resummation like this. But you see, let's say in phi to the fourth, this term here is of order n factorial squared. Okay, and if you want to have something convergent, then you see that because you want compensation, you want to resum different orders, and in fact you can argue that you need infinitely many orders for resummation. Okay. All right, so let's see if I can convince you that loop vertex expansion can do both. So we will see one of the two aspects right now. But before this, I need to tell you how I construct these weights W of G and T, and this is done with the Forest formula. So just in case people never saw this formula, I have a slide on it. So it's also called BKAR formula after Bridges, Kennedy, Abdeslam, and Rivasseau. This is a Taylor formula for with a special stopping rule. So the setting is the following: you have an integer big under 2 and a function of n minus 1 over 2 variables, which is sufficiently differentiable. And I will write Kn for the complete graph on the set 1 to up to n. And note that the number of edges of this graph is precisely n minus 1 over 2. So you have to think about this, the variables xl as attached to the edges of Kn. So here's the formula. It tells you that f at 1, meaning each variable is set to 1, is a certain sum, which pretty much looks like a Taylor expansion, but not quite. So you have a sum here an integral over parameters which are called interpolating or weakening parameters, you have a certain derivative of the function and an evaluation point. So let's look at these terms. So the sum is over spanning forest of Kn, which means you choose a subset of edges which form an acyclic subgraph of Kn. The integral over the interpolating parameters is this one. So you have one parameter per edge of the forest, and they all run from 0 to 1. The derivative is this. So you differentiate once with respect to each variable attached corresponding to each line of the forest. And now I have to tell you at which point I evaluate the derivative of my function f. So this capital X is an n-1 over 2 tuple of variables. So let me choose one which is indexed by L, an edge of Kn. So this edge has two ends, okay? So either these two ends belong to different connected components of the forest or to the same. So if they belong to different connected components, then you set the corresponding variable to 0. And if they belong to the same connected components, it means that the two ends of L are inside one tree. So there is a unique path between these two ends. And the corresponding variable is simply the infimum of the weakening parameters along this path. Okay? All right. So now let's see how you can prove a simple result using loop vertex expansion. Okay. So we'll take as model the phi-4 theory in 0 dimension. So meaning this one-dimensional integral. Okay. So you have an quartic interaction. So here phi is a real number, and mu is the standard Gaussian measure. And I'd like to prove in 2 slides that log z is an analytic function in this cardioid domain, which is pictured here. All right. The fact that z is analytic is very easy, but log z is way more difficult. All right. So I will use loop vertex expansion, and this loop vertex expansion is done in 3 steps. There is first an intermediate field representation, meaning I will change variables here. Then I will do perturbation theory in these new variables and apply a forest formula to each order. All right, let's see what is intermediate field representation. Well, it's very simple. It's also called the Hubbard-Stratonovich transformation. It's this identity, this Gaussian integral here. So if I apply this, I have a new field sigma, which has also the same Gaussian measure here. And once you've done this, then you realize that the integral over the field phi is Gaussian. So you do it because you can do. And what you get is a new integral where only one field sigma and the new potential, and this potential is this log here. Okay, and this is not polynomial. This is what makes everything work. All right, so this is intermediate field representation. Now I Taylor expand the exponential here. I interchange sum and integral, but I'm allowed to do because I have a log. So this is okay. And now I do this replication. So this v of sigma to the n, I see it. You see, I had one copy per vertex. Okay, but there is a price to pay, is that I have to degenerate the covariance. So before I had covariance 1 for my real sigma field. Now the covariance is an n by n matrix, and it's full of 1. Okay, only ones everywhere. All right, and now I will apply forest formula to test connection between these copies of sigmas. No, so I don't explain precisely how you apply this forest formula, but you recognize a lot of well, you see similarities with the formula I've shown you before. There is a sum over 4s, there are integration over interpolating parameters, derivatives, okay, and now I have a new covariance, an interpolated covariance, which depend on these evaluation points, which are infimum over the unique path, etc., etc. All right, so now one of the main benefits is that this formula allows me to compute the log very easily, because it's essentially the same formula, but where I replace f by t everywhere. You see? So instead of summing over forest, now I sum over connected components of forest, so they are trees. So I have an analytical formula I can work with to prove analyticity of log z. And once you're here, essentially you're done, because, okay, first line is just a copy of previous one. So you can compute the derivative of v. So remember, it was a log. So what you get now is a negative power of its arguments. So we call them resolvents. And here di is the degree of vertex number I in the tree. Okay, so this is this is what you get. And so you see, you have hence. So a perturbative sum at order n, you have a sum over 3. So all this expression is my a sub t that I had previously. And okay, so there is bijection, of course, between the graph, my initial phi4 graph, and the graph in the intermediate field representation. But you see that at order n of perturbation in the intermediate field, I have in fact infinitely many intermediate graphs, or infinitely many phi4 graphs, because this is non-polynomial. Okay, so this is what makes the infinite resummation, and it turns out that it works very well, because these resolvents are bounded, you know, by this cosine. So you see here appearing the cardioid domain. So if you use this bound, so you get this line. There is a bit of combinatorics of trees, but very standard, and you get that your series is converging in this cardioid domain. Okay, so this was let's say level 0 of loop vertex expansion. So now I want to jump to really the state of the art, namely the most difficult thing we can do now. So I will choose one particular tensor field. So I will show you what it is and what's the result, the proof of which I want to sketch. So now I still have complex fields, but they are of rank 4. Its complex conjugate is written T bar, and for some reason I want to write its indices as n bar. Okay, so n and n bar, bold n and n bar, they are 4 tuples. Okay, so there is a free action, a free part. So here you see there is a propagator, okay, which is very reminiscent of inverse Laplacian. And we have a cutoff for everything being well defined. So this J max, you see, you should really think it as an ultraviolet cutoff. So to make contact with matrices, this m to the J max is essentially capital N. Okay, so my indices, they are forced not to be bigger than m to the J max. All right. And then we have interaction. So now I have a large choice. So I take the easiest one. So this quartic interaction. So, but I take symmetric sum over colors. And you see here, this graph is characterized by the vertical color, so to say. So I have 4 different possibilities. I sum over the 4 different. So I take all 4 of them, and only one coupling constant. And the formal partition function, well, you see this is the exponential interaction with the Gaussian measure. But of course this is formal because I have divergences. And turns out that this model, which is nicknamed T44, is renormalizable perturbatively to all orders of perturbation. And it's not too difficult because it essentially has the power counting of phi4 in 3 dimensions, so it's super renormalizable. So we have a finite number of divergent graphs.
So I lost track of something here though, because the quadratic part was T bar, right? Or
Well,
T dot T bar,
well, it's-
which looked ultra local to me.
yeah, it's not anymore.
Oh, okay.
It's not anymore. Now, really, the quadratic part is given by this covariance. Okay?
Right, okay.
Yeah, because I have to, we need to launch a renormalization group. So I need scales, so I need a propagator. All right. So now I show you the divergent graphs. There are two-point divergent graphs. So we call them M1 and M2. Okay? So it's not very useful for the rest of the talk, but I like to show you pictures. So let's see. And there are 7 divergent melonic vacuum graphs. So you may understand all words, maybe except melonic. So you probably know that the matrix model enjoy a please.
So the quadratic part now is no longer symmetric under the action of ON.
That's true. That's true.
The whole point of the whole formula.
No, we need to break it, otherwise we can't do renormalization. I don't know how to do renormalization with a ultra-local propagator, I should admit. Yeah, that's right. You're right, it breaks symmetry. Okay, so matrix model, they enjoy a 1 over n expansion, so it's a reordering, let's say, of perturbation theory in powers of 1 over n, and it's a topological expansion. And so the breakthrough of Gouraud I was referring to is to prove that there exists also a 1 over n expansion in tensor models, colored tensor models. And this 1 over n expansion has dominant graphs. In 2D, they are planar graphs. Here, they are called melonic for some reason. Okay. And so there are 7 melonic divergent vacuum graphs. So they are here. Okay. And there are also non-melonic divergent vacuum graphs. So I show you here.
Sorry. Doesn't this 1 over n expansion assume that your Gaussian is UN or ON invariant? I mean, the whole argument doesn't that rely on that?
Yes, that's true. But still, well, yes, it's true. It's true. Right. But I haven't said that these graphs are dominant over these ones. Huh?
Could you show the propagator once more?
Oh, yeah.
Still a little confused about what the propagator is now.
Yeah.
So n is a lattice side, though.
Yes, n is a 4 tuple. So it's in Z4.
Yes.
Okay? So propagator brings you from T to T bar, so from n to n bar.
Yes.
Okay? It conserves indices, but they are not identically distributed, you see?
So why is the
It's like 1 over p squared.
so the internal symmetry is not broken, right? These UN symmetries.
Yes, it is.
No, I don't understand why that is.
Um,
There's no reason why it should be.
So maybe the confusion is there was some. I mean, you had color symmetry, UNs, right?
Yes.
Are they like flavors which are different from this n, this little n that you're summing over here?
no. My colors are this 1, 2, 3, 4.
The colors. So the colors are actually the.
Remember, the colors, they index the places of the indices of my tensors.
Yes.
So this Tn, you should imagine that it's Tn1, Tn1, N2, N3, N4.
Right.
Okay.
So we still know how to glue the faces together well using the colors, and you don't care anymore about. Originally, you had a UN symmetry, which was not a color symmetry, I guess. Originally.
No, well, yes and no. I mean, the fact that I have colors relies on the fact that my tensors are not symmetric.
Right.
Okay, and the symmetry is defined because my tensors are not symmetric.
So every tensor index has now infinitely many possible values.
Yes. Well, infinitely up to my cutoff. Yes.
Yes.
Yes, true. That's like a matrix. Huh? You sum each index from 1 to capital N, and my capital N is m to the j max. All right. Okay, so in fact the starting point is more this thing, which is the formal partition function I had before, but to which I added, of course, the divergent counterterms. Okay, so there are here the 2-point counterterms, and the vacuum one are in this calligraphic N. And I will start from this and try to prove that the log of this is analytic. So this is the result. So inside a small cardioid domain, the limit when I send cutoff to infinity of log z is analytic in G. G is my coupling constant, and this domain is independent of J max. Okay, so very similar to the zero-dimensional case, but of course with additional difficulties due to the divergence of amplitudes.
So Fabien,
Yeah.
is there a sense in which your propagator is massive or versus massive?
Yes, there is a 1. It's n squared plus 1. Yeah. Okay, so I start from this renormalized partition function, say, and first step is intermediate field representation. So I skip details, but now, so it's essentially the same as I showed you in 0 dimension, but now I have 4 intermediate fields because I have 4 colors, I mean in rank 4, okay, and they are Hermitian matrices of size m to the j max. Okay, so I have 4 big matrices, and they are my new fields. Okay, so I went to 1 tensor of rank 4 to 4 matrices of big size. Okay, so now I have a certain matrix model which looks like this. So there is well, a term delta t, which I will not comment on. This trace log 1 minus sigma, which looks very like very the same as before, and there is a linear term in sigma proportional to the mass counter terms, and the Gaussian measure on sigma is as covariance identity, right? So here lambda is square root of g. This capital sigma is essentially small sigma, but sandwiched with square roots of propagators. So you will see that we have a lot of square root of propagators everywhere hidden. Yeah.
Sorry, your interaction vertex looks like 2 sunshines with
Yeah.
the splitting corresponds to cutting those edges.
Yeah. So you know it's longer in the vertical direction, so we cut in this direction. Okay. And this sigma without color index is actually this tensor product. Well, it's not very important, but just to be clear. So now I have a new action. Okay, so what do? Now I do something I like a lot. So I pass to renormalize the action. So it's very well known, and it has like well, we know this is since 50 or 60 years ago, that reorganizing bare perturbation series into renormalized one is the same as adding counterterms in the action. Okay, it has the same effect. But still, if you start with an action which has counterterms and you want to prove that the perturbative series is finite order by order, there is some combinatorics to check. Okay, it's very standard, as I said, but still there is some work. Here, starting with this intermediate field representation, I can do very simple manipulation like expanding the log, changing variable, pushing contours, and stuff like that, to arrive at a new action which looks essentially the same but a bit different, such that the perturbative expansion of this new action is finite order by order. I don't have to look for compensation. Everything's finite in the action. Okay? So I have new variables here. So this u, which replaces sigma, you see it's simply sigma plus d1 plus d2. And d1 and d2 are essentially the renormalized amplitude of my two divergent two-point graphs, m1 and m2. Once more sandwiched with square root of propagators. And so I don't explain what is q, this is detail. And log3 is simply the remainder of the Taylor expansion of the log up to order 2, up to second order. Okay, and I claim that the perturbation series of this is finite. Well, I know that it's finite, but it's easier to see here. Well, when you look at it sufficiently long. Okay, so now of course, the proof will rely on a certain perturbative expansion, because I will need a good combinatorial factor. I mean, a good power counting factor to control everything. Let's say. So I need good control of the amplitude of my graphs, and for this, I know nothing else but multiscale analysis. So I need to multiscale decompose my action. So I slice the propagator. So C sub less than G means that the indices are smaller than m to the j. Sorry, and V sub less than J is simply the same V as before, but where I replaced all occurrence of C with a C less than J. Okay, so remember there was C here, for example, and in sigma, you remember maybe, in sigma there are C's. Each time you see a C, you replace it by this C less than J. Okay, and this is V less than J. Now my original action that I should call V less than J max is this telescopic sum, provided V0 is 0 by definition. Okay, and those differences I call them Vj. Okay, now my partition function takes this form, product over scales from 1 to J max of e to the minus Vj and the Gaussian measure on sigma. Okay. And now I want to rewrite this with fermions. So here I'm using something easy, which is I write A as integral d chi bar d chi e to the a chi bar. This is the only thing I do, and in my example, A is e to the power minus Vj, e to the. Okay, so for each scale, I use this identity. Okay, and now my exponential of Vj is in the exponential. This is W. This is 1 plus?
1 plus A.
Yeah, because it's simply that I write A as A minus 1 plus 1, and then the minus 1 I put it in a Gaussian integral here.
But I mean the identity is 1 plus A equals the integral, right? No, this is it. If I expand this,
there are two terms, and the first is 0. Okay, so why do I do these strange things? Is that because the fermions will give me some repulsion between scales, and this will be very important.
Excuse me, but this is an original idea, isn't it?
Original, but not from us, from me. It comes from a paper of Gouraud and Rivasseau, which is called multi-scale loop vertex expansion.
Ah, okay. I didn't read that one.
Okay. So I've decomposed so now this is where we stand. So we have this formula, okay, and I will do so multi-scale loop vertex expansion. So I still need to, so look, here I will do perturbation theory for this, okay, and apply Forest formula on it. But I have two kinds of links, bosonic and fermionic. So I will apply Forest formula twice on top of each other. So it's a special kind of two-jungle formula, okay. I'm afraid I'm not really, I don't have very time to explain, but it's essentially you expand your exponential. So at order n you have w to the n, okay. Then you test bosonic connection between this. So you have a forest of bosons, okay. So a collection of trees, and then you launch a Forest formula in fermionic 1, which tests fermionic connection between these trees. Okay. So result is okay. Result is this.
Excuse me. So sigma is delta correlated. There are no scales on sigma.
Sigma is delta correlated.
And chi goes with
and chi is also
scales because it's chi j.
Yes, but each pair chi bar j is also delta correlated, if you want.
And the chi j's are decorrelated one from the other.
Yeah, completely, yes. And it will remain like this. Okay, so as I said it allows me to compute the log easily. So I have a sum over some kind of trees. So there are trees with two different kind of lines, okay, fermionic or bosonic. So if you want, it's a tree whose edges bear an index 0 or 1, okay. Then you have this sum over the n scales, because you have one scale per vertex in this business. Integral over the interpolating parameters. Here, this d nu j is for jungle. D nu j is the interpolated Gaussian and Gaussian bosonic and fermionic measures. dj is a notation for the derivative, and here you have really the vertices. So b is a name for the bosonic trees, you know, because j is a tree, but it's made of several bosonic trees linked together by fermionic lines, okay. So I have usually several bosonic trees, so this is called the bosonic block, and in each block there are vertices which are labeled A. All right. So first line is the same as before. I'm already late, right?
Yes.
Okay. What can I say? So you can compute the fermionic integral exactly, and it gives you this repulsion of scales that I was mentioning before. Okay, and then the only thing you're remaining to do is to bound this bosonic part here. Okay, and there is a perturbative and a non-perturbative part that you separate by Cauchy-Schwarz inequality, and of course the main part of the work is the bounds, the perturbative and non-perturbative bound. So I don't have time to explain, but if you want to ask, I can show you. Okay. So once you've done this, you put everything together and you hope that everything's fine, and in fact, yes. Okay, so you can prove that your series is normally convergent, and you're done. You want to ask a question?
I will have a question, but I can wait till the end.
Okay, thank you. So end is here. So I would say that it might be a bit oversold, but let's say that tensor field theory provides at least a combinatorial theory of random spaces. And there has been a lot of result in the last 8 years. And regarding perspectives, we are working on the rank 5, the same model but in rank 5 with Vincent. So it's just renormalizable, but in contrast with 544, it's asymptotically free. So we have good hope that we can construct it. And then I keep the rest for questions. Okay, thank you.
I'm afraid we have almost no time for questions. Maybe one urgent one. Yeah.
You choose.
Okay. Well, my question is this about the log 3. So you took the quadratic part out of the determinant, if I understand right.
Where?
You have expanded. You have trace log 3.
Yes.
So trace of log is a nice thing, I think, because there's a determinant. It's a determinant of 1 plus I, or something like that, right? If you take the quadratic part out, then don't you get back a large field problem? That's what I'm worried about.
Well, answer is no. No. So in fact, this log 3, you rewrite it as log plus the beginning of the Taylor expansion.
Yes.
Okay.
You put them back together again in large fields?
Yes. No, we don't do any small field, large field analysis. All the point is essentially to avoid this.
Yeah.
And everything works because we have this log and its derivative is bounded. Let's say. What I didn't have time to show you is that in the perturbative part, so you have say amplitudes of graphs, okay, in front of your exponential, and these amplitudes are full of resolvents, okay, and all resolvents are bounded, okay, and that's what makes everything work. And this expansion changed nothing.
I have to do
Let's
that.
have the rest of the discussion at coffee break.
Yeah.
And let's resume early because we have a very
yeah.
short lunch today. So we want to finish the next talk also in time in order to have lunch and come for the next after that. Let's thank the speaker again.